Hello everyone, thank you for joining me today as we discuss complex numbers. In order to keep this video as brief as possible, I won't get too deep into the history of this new number for us, but I will talk a little bit about it, and then our three objectives here are to use imaginary numbers to simplify radicals, perform some operations with imaginary numbers and complex numbers, and then interpret complex solutions. So how does this fit into the curriculum for this class in this specific chapter? Well, recently we've been solving quadratic equations using square roots. Alright, so consider the equation below, 2x squared plus 128 equals 0. If we go to solve this using square roots, we'll subtract 128 from both sides, divide by 2 in order to isolate x squared, and then take the square root of both sides to isolate x, canceling out that exponent there, which gives x equals plus or minus the square root of negative 64. So we'd have to think of a number that we could square to get negative 64, and you might think negative 8 for a brief moment, but even negative 8 won't work because negative 8 times negative 8 would give positive 64, not negative 64. As it turns out, there is no real number that works here. There's no real solution to this quadratic equation. So in previous math classes you might have said no solution, but today we are going to learn a way to interpret such a situation using the imaginary number I. So let's talk a little bit about this imaginary number, just some brief historical context. There came a time when mathematicians wanted some number, they were trying to find a number that they could multiply by itself and result in a negative result there. I is that number here for us. Okay, there's a lot more historical background than that. However, just keeping it brief here, if you try to think of a real-world manifestation of this imaginary number, you're going to think a long time and not come up with a whole lot, because there is no distance, no time, no velocity, no mass. There's not really a real-world construct that we can use to represent this. But we've got to think of the imaginary number as a tool of convenience that mathematicians, engineers, physicists use to work with certain types of equations and not have to just stop when they get to a point like we got in the warm-up today, so they can carry on with their calculations and come to some real solution that shows up in the lab or wherever it is they're working. We're going to focus on the mechanics behind these numbers. That's what fits best for this class in particular. So the imaginary number I is defined to be the square root of negative 1. So then inherently I squared itself will equal negative 1. And we're going to perform a few different tasks with this imaginary number. The first is simplifying radicals with negatives on the inside, much like that radical we had in the warm-up there. We'll do the column on the left together. You can pause and try the column on the right a little bit later. Let's start with the square root of negative 11. The idea here is to take that square root of negative 11, split it into the square root of negative 1 times the square root of 11, where the square root of negative 1 is exactly what I is defined to equal. Square root of 11 can't be simplified anymore. 11 is prime and there are no perfect square factors that go into it, and thus we end up with I square root of 11. Moving down to the square root of negative 64, same situation we had in today's warm-up. We'll split that into the square root of negative 1 times the square root of 64, where the square root of negative 1 is exactly what I is defined to equal, and the square root of 64 is conveniently exactly 8. Now, just like how we wouldn't write x8 or a8, we're going to put the letter after the coefficient here. 8i is how we could represent that there. Finally, the square root of negative 40. Again, split off a square root of negative 1. We'll use I to deal with that. But now 40 is not itself a perfect square, but we should try breaking it down because 40 is not prime like 11 was. So we try to think of a perfect square that factors into 40, and you can make a list of the factors of 40 if it helps. 4 is a factor of 40 that is a perfect square. So we'll split 40 into 4 times 10, and now working from left to right, the square root of negative 1 is exactly I, the square root of 4 is exactly 2, and the square root of 10 is stuck. There's not much we can do to break that down. There's nothing we can do to break that down any further. Like before, we'll put the I after the coefficient of 2. The square root of 10 will come last just so we don't confuse anything else being inside that square root than just the 10. So there it is, 2i square roots of 10 when you simplify the square root of negative 40. I'm not going to work through every single example on the right, but I will write down the answers in case you want to try these and check them. So if you want to, now would be a good time to pause. Here are those answers if you want to try these out on your own. Anytime that we learn a new number, like when you first learned about fractions, whenever that happened to be, you then proceeded to learn how to do various operations with that new type of number. Adding fractions, multiplying fractions, dividing fractions. Well, here we'll do the same thing with imaginary numbers. We'll stick to addition, subtraction, and multiplication. But first we've got to talk about what happens when the real numbers and the imaginary numbers collide. So in the top right corner here, you'll see what's called a complex number. This is the kind of number we get when we add real numbers with imaginary numbers. A there is the real part, the real number here. BI is that imaginary part, that imaginary number. We put them together, we get complex numbers. Complex doesn't necessarily mean more difficult, it just means that it's made up of more parts. It's complex in that sense. The good news with complex numbers is that we add, subtract, and multiply the same way we do with polynomials. So negative 3 minus 5i plus 4 minus 2i will be just like negative 3 minus 5x plus 4 minus 2x. These parentheses are here just to group the parts of the complex number together. We're just going to combine like terms when we add these complex numbers together. So I'm looking at the real parts here, negative 3 and 4. We're going to go ahead and combine those. We're going to combine negative 5i with negative 2i to get the imaginary part of this complex number. So there is 1 minus 7i. Okay, let's try the one on the right here. The trap that students will sometimes fall into is thinking this is a FOIL problem because they see the parentheses there. This is not a FOIL problem. There's a plus sign in between. This is an addition problem, and we add complex numbers by combining like terms. So here 16 plus 9 is 25. 3i plus negative 2i gives us a positive 1i. With subtraction, we've got to slow down a little bit and recognize that we are subtracting everything in this second set of parentheses. So we are subtracting negative 2, which is really a plus 2. We're subtracting negative 6i, which is really a plus 6i. So now when we go to combine like terms, 12 plus 2 is 14. 5i plus 6i gives us 11i. Choosing to write my answers in this format, that's the traditional way to write complex numbers. If you wrote it this way, I wouldn't count it wrong per se. Just trying to show you what the convention is here with these complex numbers. A plus bi, the real part, plus the imaginary part. Here we're subtracting 5 and subtracting negative 10i, which turns into a plus 10i. So we combine like terms. 8 plus negative 5 is 3. Negative I plus 10i gives us a 9i. Adding and subtracting complex numbers, just like adding and subtracting polynomials, be especially careful with those subtraction problems to make sure you are subtracting everything that should be subtracted. The only other operation we'll worry about here today is multiplication. Division isn't necessarily what we need at this point in time, so we won't get down that rabbit hole here. Let's try the column on the left. Now there's 3 types of multiplication we have to be prepared to do. At the top we've got an imaginary number times another imaginary number. This is just like 4x times negative 3x, where 4 times negative 3 gives us negative 12, and I times I gives us I squared. Now that I squared though, and you can see it in the top right corner here, that I squared is equal to a specific number. Every time we see I squared, that's equivalent to negative 1. So this is really negative 12 times negative 1, which is positive 12. How about an imaginary number times a complex number? Well, this would require us to do distribution. Negative 7i times 2 is negative 14i. Negative 7i times negative 6i, that's a negative times a negative, which will be a positive 42i squared. But here again, that I squared is equal to negative 1, so we make that substitution. And you do that enough times, you'll start to be able to do it mentally. So here is my final answer now written as a complex number, negative 42 minus 14i. In the last row here, how about a complex number times another complex number? Think of it as like a binomial times a binomial, where we have to FOIL. first, outside, inside, last. So we have 1 times 8, 1 times negative 5i, 8 times I, and I times negative 5i gives us negative 5i squared. Now that the multiplication is done, there are a few steps we can take to simplify this expression. In the middle there, we can combine like terms to get 3i. And at the end of this will be negative 5 times negative 1. Again, that I squared equaling negative 1. Well, that negative 5 times negative 1 is just going to turn into a positive 5. And if we combine like terms now, 8 times 5 gives 13. 13 plus 3i is our complex number final answer here. If you want to try the column on the right, I suppose I can at least write down the final answers here. That way you can give them a check. If you want to go back and give it a go here, those will be the answers. You can check them there. So at this point, we'll skip this to save time. At this point, we have simplified radicals using the imaginary number. We have added, subtracted, multiplied complex numbers with imaginary numbers. Let's kind of bookend this and go back to the situation we had in the warm-up now, where we had a quadratic equation that had no real solution. Well, if we had tried to solve that graphically, that technique would have failed. Quadratic equations with complex solutions will not have real x-intercepts. And so while there's no real solutions to be found graphically, now that we know this imaginary number I, we can interpret the complex solutions and we can get them algebraically. Right now, the major algebraic technique we have for solving quadratics is square roots. So let's take a look at that here again. One more time. We'll make this our last example today. Okay, we want to solve this using square roots, and this is a great candidate for that because there is no linear term here, right? There's no linear term in there to mess things up. We can, in a few algebra steps, isolate that x squared so we can solve using square roots. So I'll subtract 100 from both sides, divide by 4 on both sides, take the square root of both sides, and if you were back in, say, Algebra 1 or something like that, you maybe would get here, say, oh, there's no real number I can square to get a negative, and throw up your hands and say no solution. But now, okay, we know that we can use the imaginary number I to simplify this, and to save a little bit of time, I'm just going to jump right to it. 25 as a perfect square whose square root is 5. The negative there is managed with the imaginary number I. Two complex solutions to this quadratic equation. If you check this out graphically, there will be no x-intercepts. In fact, this is a stretched parabola that's shifted up 100 units. You'll have to zoom up pretty far to see it. No x-intercepts because there are no real solutions to this quadratic equation. So today we talked a little bit about these imaginary numbers. Put them together with real numbers, you get complex numbers. We had 3 objectives with that. Didn't give a ton of historical context here. That would make our video a lot longer than it perhaps needs to be right now. In person, you would get more of that historical context. So that's enough for us today. Thank you for watching.